All right, everybody. Thank you for showing up, first of all, to this early afternoon. Hopefully the postprandial glucose levels maintain themselves, and we can all keep some amount of attention for this, the lecture. We really appreciate you being here. We obviously also appreciate the organizers' invitation for us to be here as well. We have nothing to disclose of financial nature. My name is Amrom Obstfeld, and I am the medical director of the Division of Pathology Informatics at Children's Hospital of Philadelphia, where I am also the medical director of the hematology lab. And with me for this session, I have Stephan Kadauke, who is also in the Division of Pathology Informatics with me, and is one of the directors of the Cell and Gene Therapy Lab at Children's Hospital of Philadelphia. And this is a tag team effort between the two of us. I'm going to start us off with what I'm calling the principles of pathology data science, where I'll talk more in general terms what I mean by this, what is the value that data science, in particular one specific aspect of data science, reproducibility, what that has for a value for pathology. And then Stephan will take over in the latter half of the session, and we'll discuss in more practical terms how we've kind of actualized this at University of Pennsylvania, Children's Hospital of Philadelphia, and with the trainees and faculty at HUP as well. So without further ado, the principles of pathology data science. So this lecture is going to be divided into three sections. I'll first talk about why are we here? Why are we talking about this? Why should I even bother with potentially a form of data analysis that's going to be harder to do? I'm going to have to train to do it. Why can't I just, use the practices that I've been using as I've kind of come up? Then I'll talk about what is data science? What does it have to offer? How does it solve our problems? And then finally, I'll talk about some specific practices that enable this feature of data science, which I've called reproducibility. So why bother with data science? Some of you might be aware, just from the lay press or even the scientific press, that we are in a period that's been called a reproducibility crisis. So we've seen this phenomenon play out both in the scientific press with prominent journals taking notice of this quote-unquote crisis, but also the lay press also kind of keying in on this. And this is a frustrating trend where results of landmark studies with very splashy results published in some of the top-tier journals in the world, really, that are coming from the most prestigious universities that we have in various fields of scientific research just cannot be replicated, okay? And in fact, this is no trivial issue. In fact, in pharma, it's kind of the unspoken conventional wisdom that at least 50% of the studies published, even in top-tier academic journals, just can't be repeated. Now, generally, pharma companies are pretty private about their data, their internal data, and it really wasn't quite clear how true that conventional wisdom was until Bayer had had enough of this and published a startling paper. And this is a figure that actually came from Wall Street Journal, which did a write-up of this study. But essentially, Bayer reported that based on their internal data, 2/3 of studies that they attempted to replicate, these were published in top-tier journals, just could not be repeated. Now, they obviously care about this because they're in the business of bringing ideas from academia to the market. Their most significant issue here is, their bottom line. They're losing money, and but in effect, the real problem here goes a lot deeper because this really calls into question the scientific practices that we all use. But even more importantly, the reproducibility crisis is having an impact on the credibility of science and the credibility of data. So essentially, if anyone can bend data to their own will, then data ceases to have value. This crisis has multiple causes, including cherry picking of results, use of inappropriate statistical methods, but a significant contributor has to do with the practices that we use as we analyze our data. And I thought I would illustrate this with two case studies. So the first vignette is the Anil Potty Duke cancer scandal. I'm just wondering in this group here, how many have heard of this scandal? So, a strong minority. Fantastic. So now you're all going to have heard about it. And I actually tell this story to just about every trainee that I teach any kind of informatics content to. So Anil Potty was a budding hematologist oncologist, product of Duke's fellowship program. He stayed on there as faculty, and he continued in this translational research lab. And this was the mid-2000s when microarrays were all the rage, and Potty dedicated his efforts to achieving what I would call the holy grail of personalized medicine. He claimed that he had found a gene signature that would predict which patient would respond to a chemotherapy and which patient would be resistant to that chemotherapy, right? This is the ultimate in diagnostic testing, certainly from our perspective in pathology, I think. And the scientific literature just ate this stuff up. They published in the top journals that we have, including New England Journal, JAMA, and you can see the rest. And this research was really taking off, and they were ready to go to the next level. So they started a clinical trial, in fact, several clinical trials. And they took essentially 100 patients with advanced cancer, various types, who had no options left. These patients threw their lot in with these researchers, and they had their chemotherapy regimens chosen by this microarray-based gene expression-based algorithm. But the edifice here that they had kind of constructed was built on a defective foundation. And slowly at first, but then very quickly, almost all of those publications had to be heavily corrected or retracted altogether. A total of 18 high-impact manuscripts to date. And this was all undone by two statisticians at MD Anderson, Keith Baggerly and Kevin Coombs, who began with a very simple request. They wanted to see the data. They wanted to see what Potty had done so that they could see if they could reproduce the results. And this wasn't, in any way malicious. They wanted to apply that approach to their area of interest there in MD Anderson. And this set off kind of a very malignant back and forth with the researchers. The whole story kind of playing out at this point can be found on the internet. Eventually, they persisted and did get access to that data. But the issue was they couldn't make any sense of what was going on there, right? They couldn't reproduce the results. There was little to no documentation on what the original researchers had done. So, you can just imagine, we have a room here of pathologists and laboratorians. I think that many of you probably kind of react to this with a gut reaction of how could this even have touched the patient, right? The kind of requirements that we carry with ourselves as we validate new testing. How could scientists who had essentially a black box that was, turns out, quite faulty black box, have applied that to patient care? Anyways, Baggerly and Coombs went about essentially finding clues in the analysis and reconstructing what Potty had done. They essentially invented a new field, and they called it forensic bioinformatics. They had to do a deep dive into whatever documentation. Obviously, the method sections of these papers was a joke, and whatever results that they had access to, and kind of retrace the analytical steps that the Duke scientists had kind of taken. And what they found was highly disturbing. So for instance, Potty had claimed that expression from a few dozen genes could predict whether a tumor would respond to a chemotherapeutic agent, adriamycin, all right? And what Baggerly and Coombs did is they took the same data and they clustered patients based on their gene expression that the researchers claimed that they had used, and they made a heat map to see how patients had kind of sort of self-sorted themselves into these clusters of responders and non-responders. Now, I don't think we have to be bioinformaticians here to look at this heat map and say that this is just noise. There is no pattern here, right? Between the blue and the red, the non-responders and responders, there is absolutely no pattern. But there is a far more significant issue that's going on here that they have actually highlighted. This is a figure from their paper in these purple boxes. And what they're showing you here is actually samples from this microarray that have the exact same gene expression. Okay, so this is duplicated data that went into creating this gene signature, right? That is not something that you're allowed to do. But even more so, we have a problem here, right? Inside some of these boxes are these duplications, or sometimes triplications and quadruplications, are samples that are labeled both as responders and non-responders, right? So some of the replicates look like they were labeled as responders and some of them as non-responders, right? This is a complete mess from an analytical standpoint. And how does this happen? Well, one of the things that could happen is you could have an issue like this, which is called an off-by-one error. Basically, what Baggerly and Coombs did was they lined up gene signatures from their analysis and Potty's and found that the labels for those gene signatures didn't exactly match, right? We have on one side 1881 and the other side 1882, right? And so on and so forth. What do you guys think is going on here? Yeah, this is an off-by-one error, okay? This is what happens when you copy and paste data from one worksheet to another, in which one there's a header row and in another one there is no header row, right? You get an off-by-one error. Of course, this could happen whenever you copy and paste something between two programs. But that's not the most damning accusation from Baggerly and Coombs, because it's one thing to make mistakes. We all make mistakes, right? Certainly we wouldn't want those mistakes to affect patients, which they also allowed to happen. Their most damning accusation was that there was just poor documentation and a complete lack of reproducibility, right? It was impossible for a third party to go in there and see exactly what was done so that this kind of critique could happen in the first place, right? This is what should have happened way before any patient had seen any of this. And they note in their paper that these mistakes are easy to make, particularly if working with spreadsheet programs like Excel. Now, lest you think that this is a problem specific to biomedicine, it actually pervades anywhere that people use analysis. And I've chosen actually another vignette, and this is coming from the world of economics. Carmen Reinhardt and Kenneth Rogoff are two very prominent economists. They did work at Harvard at the time that this was published. I'm not sure they're still there. And they published a paper called Growth in a Time of Debt. And the central question of the paper was, is economic growth affected by government debt levels? And they came up with quite a controversial finding. They found that above debt levels of 90% of GDP, median growth rates in GDP for that nation tended to fall. Now, why was this so controversial? Well, this came about during the economic crisis in the late 2000s, early 2010s, and that we called that the Great Recession, obviously. And there was a very significant policy question that was going on at the time. Should governments in this situation spend more in order to drive up demand, or should they spend less in order to reduce overall debt levels? And this finding really reverberated around the world at the time. And it drove policy in the EU, in Great Britain, and in the US as well. In the EU, it was called austerity. In the US, we called it the sequester, right? The limitation on spending by government in that situation. Now, the only problem here is that the finding wasn't quite true. And it took a grad student from the University of Massachusetts to get the raw data from Reinhardt and Rogoff, and he found several errors, including, crucially, a spreadsheet error. Namely, the authors somehow managed to exclude 5 countries from their calculations. These were Australia, Austria, Belgium, Canada, and Denmark. Does anyone notice a pattern here? Yes, right? Alphabetical from A to D. Exactly right. So what happened? Most likely what happened is that someone had used a mouse to draw kind of a gate around the cells that they wanted to include in the final calculation and just didn't go all the way to the end, right? And what's the result of that error? Well, actually, GDP growth is positive 2.2% at high debt levels, not negative 0.1%, okay? So this was a very significant error, one that many economists now ask, how many people are now unemployed because of this very simple Excel error. But what I'd like to kind of pose to us and to myself, are we any better? It's quite easy to say, well, I'm careful when I analyze my data. Whenever I use Excel, I make sure to put little notes about what I'm doing. But who hasn't asked themselves questions like, Where did I get these data from? How did I create this plot? How did I process this data? Why did I decide to omit these samples from the analysis? So data analysis is part of the practice of pathology, right? Whether it's measuring our turnaround times or validating new testing, maintaining QC on our instrumentation, data is the basis for every key operational, quality, and clinical decision that we make. And that's why we have to insist on the highest standards in data analysis, right? So right now, we're the guy on the left, right? How do we get to be more explicit in step 2? How do we get better? And the answer is that we need to adopt more rigorous practices. And these practices have been developed as part of a newly developing field that's called data science. So let's discuss what actually is data science and what can it contribute to this very significant issue of reproducibility. So in order to tackle this concept, what I'd like to do is actually separate it into its 2 component words. Let's deal with data separately and science separately. We've all heard this, or many of us may have heard that data is the new oil. This analogy, while not perfect, what does that mean? It really comes from the fact that these things are very plentiful. Both data and oil are all around us. They can be hard to get sometimes, but they are all around us. They both have intrinsic value, but in order to get at that value, you have to put work into them, right? The data has to be refined in order for us to really gain some pearls from it, some knowledge from it. And of course, this is happening in the context of what we're calling the age of big data. This is a term that gets thrown around a lot, but it does have some amount of meaning that's been given to it by the, people on the internet, I guess. But what kind of falls into this term of big data is data that has the characteristics of what's called the 4 V's. The first is volume of data that we produce. It's immense as a result of more and more of our activities being digital. Certainly in the healthcare world, our data is in the EHR or in our LIS. Our slides are being digitized. All this is leading to a tremendous amount of data being out there. It also has to do with the fact that data comes in a large variety, right? We're used to seeing data that's in rows and columns, but we also have text data, and we also have imaging data, and flow cytometry data, and various other kinds. Third, it's velocity. Velocity means that the data is coming at us very quickly, right? We have to process it in a live fashion. We can't just wait for a month and then look. And fourth is veracity. And this is somewhat less applicable in the healthcare space. It has to do with the fact that certain data has sort of questionable truthiness to it, I guess. This is particularly true in the context of data that you might find out on the web, in Twitter, for instance, but it does apply to clinical notes, for instance, where the veracity of exactly what you're reading there may not be true given copy forward and all of that. But data is not a monolithic thing. Data kind of comes in its own kind of forms, and there's this framework that's been promulgated called the DIKW framework, which stands for Data, Information, Knowledge, and Wisdom. And in this framework, data represents the raw measurements. An example would be like your glucose level. Information is data in context, right? That could be like a trend in the glucose. Knowledge would be information with meaning. So high glucose or rising glucose, that's indicative of possible diabetes. And then finally, we have wisdom at the highest level. That would represent something like knowledge made ready for action. What are the treatment options here? Given the patient's particular biology, but also their response to therapy, but also their specific sociological or socioeconomic status, what's the right thing to do for this patient? And these terms don't actually just sort of exist in a linear fashion, but actually are put into this rubric where data is the most basic one. It's the least challenging to get access to. It's also the least refined and has least value. Whereas information, as you go further up, you get increased value, but it becomes harder and harder to get access to it. And so the question becomes, how do you get from data all the way up to wisdom? What's the mechanism? So the answer is that data analysis is the way that we do that. And of course, data analysis comes in different forms as well. Data analysis will come in different forms depending on the specific use that you're trying to get out of that data, right? And I would call this kind of data refinement, right? How far are you going to go to refine that data in order to help you drive the answers to questions that you have. And in fact, that's the framework that was put forth by two biostatisticians at Johns Hopkins at their School of Public Health, Jeff Leake and Roger Pang, who are really leaders in this field of data science and reproducibility. And what they've done is they've said, ask yourself, what is the question that you're trying to ask of the data? And then we can figure out what the right way to approach the data analysis is. Is your question, what was my turnaround time like yesterday? How many stats did I get yesterday, right? You're probably going to be sufficed with a typical data analysis workflow that you've been using. But if your questions are getting a little bit more complex, you're probably going to have to use additional statistical tools. For instance, is there a relationship between my turnaround time and my staffing levels? Do stat volumes correlate with ED census, right? You're starting to ask the why questions. And finally, data science really asks the sort of highest level questions relating to what's happening in the future. Will increasing staffing levels reduce my turnaround time failures? If the ED grows in terms of the number of beds that it has, what can I expect from my stat volumes to happen? So what we're seeing here is that data analysis is intrinsically historically looking. It's looking at what's happened in the past. In classical statistics, you're looking at statistical significance. You want to see whether two things are correlated with another. But in data science, you're really looking for operational and clinical significance, right? Will making a change have some impact on what I do in the future? It's answering operational questions. And the hope is that it could provide generalizable conclusions and predictions. So what does this all have to do with science? Well, science is a mechanism that builds knowledge based on an iterative cycle in which hypotheses are proposed, tested, and independently verified through a process that we call replication, right? And in fact, data science is much the same. As defined by the National Institute of Standards and Technology, data science is the extraction of actionable knowledge directly from data through a process of hypothesis formulation and hypothesis testing. But of course, the linchpin to all this is replication, especially the linchpin of science is replication, right? Replication is the process in which you collect new data and in which you test whether that new data supports the original hypothesis or whether it refutes that original hypothesis. That's the scientific gold standard. The only issue is that it is very difficult and time-consuming. When it comes to data analysis, a more modest but necessary quality check has to be met, and that's reproduction, right? When we have reproduction, that means that another person can regenerate the same exact results, the same figures, the same statistical test results without any involvement from the original analyzer of the data. In short, the analysis should stand on its own. All of the reported results should flow directly from raw data and the analysis that was applied to it, completely independent of the person who happened to be analyzing it. Something that we take for granted is that an observation cannot be replicated, cannot be considered science. Well, I would argue by the same token that an analysis that cannot be reproduced cannot be considered data science. So how does one ensure reproducibility in one's data analysis? So what we can do is look to, this is the classical Venn diagram of data science, the three major skill sets that any data scientist or person analyzing data as a data scientist must possess. It's composed of substantive expertise, math and statistics knowledge, and hacking skills. Substantive expertise, I think we would call subject matter expertise. That's how we tend to think about it. That's someone who's going to be asking the right questions, who's going to be providing that sanity check to that data. Math and statistics knowledge, well, you have to use the right methodology. Otherwise, the results from the testing is going to be completely bogus. But what's this hacking skills thing? Hacking skills, I think, initially meant some kind of IT acumen or something like that. But I think to put a kind of a sharper point to it, it's a set of technical practices that enable the consistent and reproducible use of statistics to answer questions based on data. That's hacking skills. So let's discuss what practices in data science precisely do this, right? What are these hacking skills that I'm referring to here that help elevate a data analysis to a data science, to something that is analytically reproducible? So what are the principles of good data science? What I'm going to do in the next part of the lecture is kind of compare and contrast two methods of data analysis. One is I kind of call the classical one. It's the spreadsheet-based one that we're kind of all used to doing, I think. You manipulate data in a spreadsheet with a point and click or a copy-paste. And there tends to be a lot of data entry, data manipulation, data visualization, and it all happens in one file, right? You have one file that handles all of that analytical work. And I'm going to be comparing that to a second way of doing data analysis. Hint, this is the one that I think is the better one. Okay, and it's using a different set of tools. You're going to be using, in this context, a scripting language. All right, so this is a language that uses flat text files to analyze data using functions and commands. So what are the principles of good data analysis? These are the four principles that I would argue are absolutely required to make a data analysis a good data analysis. And the first one is documentation. What that means is very simple, like what it sounds, documenting exactly what you did in that data analysis. I don't know if you've ever been in this situation. I certainly have. You get data from a database or from some other reporting tool. Maybe someone in the IT group has sent you some data, and you do a whole bunch of analytical steps, and then you wind up with the charts that you wanted. I've got my charts. But then when you look back at it, you're like, what exactly how did I get here from that original starting point, right? That's happened to me many times. And what I tried to do initially when I was using Excel to do most of my data analyses, I would do something like this. I'd kind of keep careful notes and kind of refer back between my spreadsheet and my little notepad document where I was kind of noting exactly what I had done over the course of that analysis. And the issue there is that you run into a situation like this, right? So if you want to draw a horse, very, very simple, right? You draw a couple circles, so you draw the legs, then you draw a nice little face and the hair, and then you add some details, and then you have a horse, right? That's the situation where I can continue to find myself in this situation where I could not, right, really be precise enough with this documentation. And those proponents in the kind of data science world like to compare spreadsheets to something very apocalyptic. Spreadsheets are a dystopian moonscape of unrecorded user actions, right? It sounds absolutely horrible. But the idea here is that when you're working with a program like a spreadsheet program like Excel, there are numerous data analysis steps that you're taking that are just not recorded because you're pressing a button or because you're dragging something. And it's not your fault, it's the program's fault for letting you do things to your data that you're not going to be able to retrace later. So I'm going to compare that with how it might work in a scripting program. In a scripting program, it works very differently. You're working with a notepad document, and in that notepad document, you are using the commands that are built into that scripting program for the analysis to happen through those functions. Now, I would admit that this is less legible than perhaps my scribbles on a notepad, but the truth is that nothing can happen to this data that I haven't written here. So I know precisely what happened. And even maybe some of the more adventurous people here might see that there's some filtering going on here and some renaming going on. So the scripting languages do have that asset in that they're not completely a black box in terms of how it works. The next fundamental principle I'd like to discuss is transparency. And that simply means describing why you did what you did. This is certainly feasible in the context of a spreadsheet program. You can put little comments in, you can say, okay, I removed this sample, it's an outlier, machine was off that day, I'm not going to include it. But it's certainly kind of less elegant than this kind of approach where you can essentially just put text directly into your little notepad document describing exactly why you're doing this analytical step. Well, you can put a whole paragraph in there describing why you removed that sample. The next general principle I think that's very important is automation. Any good data analysis should be able to be run on the data that you're giving it, but also the data that you're going to get tomorrow, the data that you're going to get next week, the data that you're going to get next month. And it should just go directly into that analytical program and give you that result again and again and again. So what this is basically saying, and this is kind of related to what I told you earlier, the raw data and the analytical instructions should give you the results without any input from you. And if you think about all the various steps that we take as we analyze data, if you can really box it into various categories. You start with raw data. There's usually some amount of data cleaning that goes on. You might want to actually push something out to say, these are some weird data, I'm going to put them aside for a second. Then there's some statistical summaries that might happen, some data visualization that might happen, that might get stitched together into like a final report that you're going to be sharing with your colleagues or your superiors. Each one of these should be in its own compartment and completely automatable via one of these scripts. And finally, version control. Version control simply means that you should be able to describe what you did when you did it. Now, this is something that lives already within our LISs, within all of the analytical systems that we already use for clinical care. You have to be able to retrace exactly what the, for instance, reference range was when you made it live, when you took it out of production. The same thing should play into these kinds of analyses. You need a method to record the changes that have happened to that analysis over time. Now, if you're working with Microsoft Word to do these data analyses, this is going to be a little bit challenging. And I know this because I made this presentation in PowerPoint, and this is how I did my version control. And I have like a million different now, a lot more than this list in terms of versions of this PowerPoint, and it can go on and on. I think that Google does a little bit of a better job of this. It actually does have a very nice kind of version control or revision history. You can actually go back to the way that it looked when you sent out that informatics elective rotation description to the residents and tell them exactly what you said that you were going to do to them or do with them. Excuse me. It's not that funny. When working with scripting languages, there are a large number of tools that you can make use of in order to maintain version control. And one of the kind of approaches is called Git, and there's a product called GitHub. It's essentially free on the internet, and this is a way to track changes in ASCII text. It's got to be sort of a bare bones kind of notepad type of text. But you can actually see exactly what your script looked like over various periods of time. So these are the principles of good data analysis. I would say that sort of inverse, there are some principles of bad data analysis. One of them would be pulling data by hand. So if you're pulling data by hand, you're going to be pulling data by hand every single time, and you're going to be asking yourself, well, how did I fill in that dropdown? Did I include those, did I put a checkbox in that little check mark in that checkbox or not? Using the mouse, this is once again getting to that idea that it's impossible to record actions that you're doing to that data. Analyzing with buttons. This is something that is very poorly recorded in Excel, for instance. And then finally, saving figures instead of the steps. When I do data analysis now, I actually never save results because the results are exactly what you want to avoid. That's exactly what you want to be reproducible. So I should be able to get rid of everything I just produced, open it up fresh, and the analysis should come right out of the script that I just wrote. So in short, if you're going to do this, I think this is what we're going to think. That actually looks a little like you. So in short, you mostly collaborate with yourself, and me from 2 months ago never responds to email. So if you've ever been in a situation where you're going back to an Excel spreadsheet that you put down for a week, a month, or a year, and you expect, and you weren't able to understand what you did, well then this is an approach that you might want to pay attention to. So with that, I'm going to hand this over to Stephan. Stephan is going to talk about exactly how we've implemented this approach at Penn. As you might imagine, there's some hesitancy towards giving up Excel and working with another kind of program, especially if you are using terms like coding and programming. But I think that we've come up with a framework that is very understandable and digestible for pathology professionals and laboratorians. So I'll let you take it away.
Thanks, Amrom, and also thanks to the organizers for inviting us to speak here. And I guess you're right, Jean-Luc Picard looks a little bit like me. Okay. All right, so I want to start with a disclaimer. I'll be using some materials in my talk that are borrowed from RStudio, a company in which I have no financial interest and I'm not getting paid to promote commercially. I think these guys just simply are doing some really great work, especially in the educational space. And they're developing a lot of the free open source software that we use in our daily work and that I use in my teaching. All of the software and the materials I'm going to be talking about today from RStudio is completely free and open source. And with that in mind, here's the outline for my portion of the presentation. I'll be introducing two concepts that you may be unfamiliar with, that of computational documents and that of the Tidyverse. And as I'll explain in greater detail, a computational document is a document that has executable code inside of it. And I'll explain why that has some major benefits, not only for reproducibility, but also implications in the entire workflow for data analysis and pathology. And the Tidyverse is a recent dialect of the R programming language, R as in the letter after the before the letter S, yeah. The Tidyverse is a dialect of R that focuses on human readable code. And at the end of the talk, I'll spend a few minutes talking about a course in reproducible clinical data analysis that Amrom and I have been teaching to pathology residents and faculty at our home institution. So computational documents. Computational documents are a key technology for reproducible data science. And essentially, there are plain text files like the ones Amrom talked about that have both English narrative and executable code inside of them. And I'm just going to start with a little bit of a demo to show what it is that I'm talking about. So this here is a computational document. So you can see it's a text file. It has some text in it and also has some executable code. And if you author a document like this and you send it to someone else, then this allows the reader of the document to run the code. And as someone who knows how to write code, you can write anything in here that you'd like the reader to be able to do. This document contains a simple data analysis that turns the results of a survey we did of our course into a series of bar plots. And anyone who receives this document can reproduce the entire analysis. So you can run the code. You can see there's some things happening under the hood here. We're creating some bar plots. Okay, a little pie chart here. And we can knit the document into a variety of different formats. And when I do that, just bear with me for a second. When I do that, it creates a finished presentation that you can pass on to someone else. So a computational document contains embedded code, and because it does, it can automatically reproduce an analysis. And not only can we reproduce the analysis, as Amrom had explained earlier, we can reproduce the analysis automatically. And that automation creates opportunities for labs and pathology departments to create not just ad hoc reports, but also repeated automated audits and fully automated dashboards even. And this is going to be a disruptive technology that will challenge how people think about analyzing data. And it's been suggested that just like the Gutenberg printing press made it useful for people to learn how to read, computational documents will make it useful for people to learn how to code. So to recap, the two main benefits of computational documents are, for authors, you can generate reports more efficiently because you dramatically cut down on the time that it takes to do repetitive work. But there are also benefits for users because they can now interact with content in new ways and in real time. There are multiple ways to create computational documents, but for the remainder of the talk, I'll focus on just one, and that's called R Markdown. And the example document that I've shown to you is an R Markdown document. So R Markdown documents contain three different types of content. So you have your text. So this is just English text that you type into the editor. Then there's code. And the code always starts out with these 3 backticks and ends with 3 backticks. And the editor here highlights where you have chunks of code. And a header. So the header specifies what the title is and some parameters for how the document should be rendered. But because it's a text file, an R Markdown document can be opened in any type of editor. But the best editor for R Markdown is the RStudio integrated, oops, that's not what I want to show, is the RStudio integrated development environment, which you can run on a Mac or on Windows. You can even set one up behind the firewall of your hospital system if you want to analyze data in a HIPAA-compliant environment. So the RStudio IDE lets you run bits of code. And that is just tremendously helpful as you build your data analysis piece by piece because you get instant feedback of whether the code is working in the way you think it is not. So we looked at the knit button already. So it provides, the RStudio IDE also provides this knit button at the top of the document and that'll allow you to create a new file with the exact same contents. So we already saw what it looks like to knit to HTML. Now, HTML is a document format that you can open in any web browser and you can publish it on a website. But you can also simply email, so it created this .html file, which you can simply grab like this and email to a collaborator, and they can look at it. They can actually download the R Markdown document from inside of that document and edit it and send it back to you. You can also knit to PDF. And that might be useful for printed reports. Let's just wait until this comes up. Let's try it again. So here's a PDF that we just created from the same code that has the same content as the HTML file. You can even knit to Microsoft Word. And these are just some defaults that are built into this button. But the truth is that you can render your R Markdown into any number of different file formats. Word document is coming up right now. Here we go. So here we have a Word document with the results of the R Markdown document with all of my graphs in it. So these PDF, HTML, and Word are just 3 examples of a huge range of different formats that you can render your R Markdown into. So it's a HTML, PDF, but you can also convert your R Markdown into a book, or into websites, or into handouts, or into presentations. You can even render your R Markdown into a BI kind of dashboard with Flex Dashboard. And you can go to this website to learn more about the different formats that you can turn your R Markdown into. So to recap, the strengths of R Markdown as a computational document format is that you have plain text files. So it's very portable. There's no risk that they won't be readable sometime in the future because the underlying software is no longer supported. Amrom talked about version control and ASCII text, so that's exactly the format that is ideal for version control, where you can see differences easily and compare differences as you make them. It has embedded code, and what I didn't show you, it's not just R that you can embed. You can also embed Python and actually a bunch of different programming languages in there if you'd like to. There's this notebook interface that lets you test code as you build your document, which is tremendously helpful as you're putting together your report. And even though you're writing a plain text file, you can render into any number of different formats, including dashboards. So if you'd like to learn more about R Markdown, here are a couple of free resources that I would encourage you to look at. This link brings you to a self-paced tutorial in R Markdown created by RStudio, which takes less than an hour from start to finish to go through. For more details, the authors of R Markdown wrote a book that was just published, and it's available for free in its entirety online under this link. So it's a very readable introduction and describes features of R Markdown in detail. So this brings me to the second major concept that I will need to introduce, the idea of the Tidyverse. So let's take a step back and ask, why would you want to learn R, and specifically the Tidyverse dialect of R, over, let's say, a more general purpose language, general purpose programming language like Python or C++? So I just want to spend a few minutes to try to convince you that there are some very compelling reasons to choose R in the Tidyverse dialect, because at some point you have to make a decision for your department or for your group on what's going to be the standard language or just standards that you want to adhere to. Okay, so if you think about what you do in any data analysis, it'll probably boil down to something that looks like this. Say you have a data set with some lab data from which you want to get some insights. So first you have to import the data into your analytics software. Then you tidy the data, by which I mean reshaping it into a format where, typically a format where rows are observations and columns are variables. But this also includes janitorial work like identifying and fixing data problems and verifying that the data really means what you think it means. So there's just an important QC step in here. Usually the next step will be to transform the data in some way. Perhaps you'll want to filter out patient visits from just a specific year to focus on. The two main engines of knowledge generation are visualization and modeling. Visualization such as plotting the distribution of patient ages, or just making things up here, and modeling such as calculating some summary statistics like a mean and a standard deviation, or creating a linear model to describe the relationship between two variables in your data. And a key point here in this model is that in a typical data analysis, transforming, visualizing, and modeling happens not just once, but many times over. And this is what's called the understand cycle. The quality of the analysis and kind of the amount of sophistication you can build into a data analysis critically depends on whether you can engage this understand cycle a sufficient number of times to get a comprehensive look at the question that you posed. The final critical piece is communication of the insights in such a way that they eventually get turned into action. So most of the time, data analysis happens collaboratively on some level. So again, we have the diagram down here, and now we just added some of the players. So oftentimes there is a domain expert who defines the objectives of the data analysis and eventually is responsible for communicating the results. And there's a technical user who actually does most of the analysis work. So sometimes this is the same person, but more often than not, it's going to be more than one person working on analysis, especially once they become more involved. So for example, let's just take an example. Let's say this is a lab director who asks a staff member to compose an audit of last year's transfusion reactions. And so maybe the lab director will send the technologist a list of patients who've had a transfusion reaction with dates, and then the tech will do some data cleanup maybe and manually look up each patient from the EHR and pull out the data that they think are needed for the audit. And when this work is done, the tech will send an updated list or a new list back to the director. And I call this the waterfall model of data analysis because as it progresses forwards in just one direction and in stages. And usually these stages involve an Excel document being emailed, so this is fundamentally non-reproducible. And some additional problems are that, if you look at the data cleaning step, this may happen entirely without the lab director's input. So this creates a risk that data problems may remain undetected. And also you don't really engage the understand cycle unless there's a lot of back and forth, which is what ends up happening. But you're really not driving this cycle in this waterfall model. So the types of analyses that you can do with this are really limited in sophistication. So in our experience at CHOP, data analysis works a lot faster in general if everyone can look at the narrative that explains the analysis, the code, and the results from the code at the same time and interact with the data in real time. And this is made possible with the use of computational documents. So R Markdown is an ideal framework for that kind of collaborative data analysis. So advantages of this agile model or this agile approach are that the analysis is fully reproducible at all stages of its development. Data quality issues can be caught earlier since the domain expert actually looks over the shoulder of the analyst as these things are being written. And you can really drive that understand cycle more rapidly, which ends up leading to a more sophisticated analysis and crank it out in a shorter period of time. The big challenge of this agile model is that it requires that some people who don't professionally, who are not trained to read and write code, must at least be able to follow along some code so they can be part of the discussion of what the analysis actually is. And this, I think, will work best if the code is concise with limited cryptic characters and as close to human readable as possible. And here's why under these circumstances the Tidyverse wins. Because the Tidyverse is the most serious and complete attempt at a concise human readable programming language for data analysis. So let's take a step back to unpack this idea. The purpose of a computer language is to transform human thought into machine language. For example, if you know C++, you can write code in C++, and the C++ compiler will compile that code into machine language. C++ is designed to be very close to machine language for a number of reasons. So a lot of the code that you write actually reflects things that are going on inside of the computer CPU and memory. So let's look at R. R is another programming language, but it was written with a specific user in mind, with a statistician or data analyst. So for these specific purposes of statistics and data analysis, it actually is really excellent, and it's much more human-friendly than C++. The Tidyverse takes this even further and provides a number of very simple and consistent language idioms on top of base R that each do one specific task well, for example, loading data from a file or plotting a graph. And because of this, the Tidyverse style of R is the easiest programming language to learn for somebody who's not primarily interested in programming or in learning programming, but in analyzing data. Because it's a very friendly and intuitive way to perform some very powerful data analysis tasks, stripping away a lot of machine language idioms. And importantly, in the background, most Tidyverse functions run highly optimized C++ code, so you get the friendly user interface without sacrificing performance. So what's the Tidyverse? The Tidyverse is a growing collection of R packages And a package is simply a zip file that contains code that implements functions that can extend the functionality of R. So the Tidyverse is a growing collection of R packages that share a common philosophy of data analysis and embed best practices in there designed to work together. So one guiding principle, or two guiding principles of the tools in the Tidyverse, is that they should be simple. Simple things do one thing and do it well, and they should be composable, meaning that that simple steps can be tied together for multi-step operations. So I want to take a very cursory look at at actually two packages. So here, the first one is the dplyr package, which provides functions for data transformation, similarly what you might be used to do manually in Excel. For example, arrange reorders the rows of a table. Filter and select, extract rows or columns respectively. Mutate computes new data columns from values in other data columns. And summarize computes statistical summaries. Each of these functions performs a simple atomic operation in a data set and also has a fairly intuitive name. dplyr allows you to compose these atomic functions into a pipeline with the pipe operator. The pipe operator, written as %, greater than %, allows you to create pipelines like the one I'm showing here. And this is actual real R, Tidyverse R code. So you can read the pipe operator as then, and so this code would be read: take the labs table, then select the age, sex, and result columns, then filter for rows where sex is equal to F, then arrange the table by the value in the result column. So dplyr allows you to reproducibly define arbitrarily complex combinations of data transformations in code that sounds almost, if not quite, but almost like English. I want to give you another example, and that's how to create graphics in Tidyverse using ggplot. ggplot implements a grammar of graphics, so GG is grammar of graphics, that will allow you to create any kind of graph by supplying three things: by supplying the data, by supplying the so-called geom function that defines the type of graph that you want, and by supplying aesthetic mappings, which are a set of specifications that tell R how the variables in the data should be represented as graphical markings on the plot. So the idea is that there's one simple template into which you can plug these three things, and you can create any plot you could think of. Now, but then you can go further and compose a plot of multiple layers of plots by combining ggplot functions with each other and create arbitrarily complex and customized figures. So this is really just a whirlwind 10,000-foot overview of the Tidyverse ideas. But if you want to learn more, there are some free resources here. Our studio, the company, publishes regular webinars, and the ones that I would highly recommend for folks that are new to R are behind this link, The Essentials of Data Science. Then R for Data Science is an incredibly well-written and complete introduction into doing data analysis with R using Tidyverse idioms. And it's available as a physical book, but also for free online. And then last but not least, Amrom and my course in reproducible clinical data analysis with R and R Studio, where the materials of which are available for free on this GitHub page. And I'm going to spend, and this course teaches building computational documents written in R Markdown. And I'm going to spend just a few minutes to tell you a little bit about our course. So this course is specifically intended for clinicians. And when I say clinicians, I include medical students, resident fellows, and attendings, nurse practitioners, but also technologists, supervisors, managers, and ancillary personnel, pharmacists, who are responsible for analyzing clinical data in some aspect of their daily work. and who are familiar with Excel for doing this, but want to learn a more efficient way that's also less prone to errors. So here are the stated goals of the course to better appreciate reproducibility in data analysis and to learn a practical way to analyze clinical data reproducibly. And by the end of the course, participants should be able to define reproducibility, and they should gain confidence in their ability to use R and RStudio to import data from files, transform data, and visualize it, and be able to create a simple reproducible report or computational document written in R Markdown. So the entire course fits into a one-day workshop, and we use active learning techniques such as concept mapping, timed interactive exercises, most of which involve live coding and pair programming in R Markdown. Together, these in-class activities get participants to a point where they can follow along the code of a reproducible report that's written in R Markdown. And here's an example of such a report that examines the reference ranges of ESR tests based on a sample of tests run at Penn. You can see there's some graphs in here, some pretty graphs with colors. So, and this is a completely reproducible self-contained document that starts with the raw data and spits out all these graphs at the end, which is kind of what we've been talking about throughout this session. So we invited our participants to complete an optional course project in the form of an R Markdown document that addresses some clinical question or some research question. And in one case, a pathology resident, Lisa Zhang, with no prior coding experience, was able to construct a machine learning model to better triage peripheral blood flow cytometry specimens. And this work was presented in a platform presentation at ASCP and in a manuscript is in press at the American Journal of Clinical Pathology. So that all got started in this course. But other residents have worked on susceptibilities of ESBL, E. coli, and K. pneumos, or triaging marrow specimens in molecular diagnostics. So people really came up with their own ideas and their own projects and put them together very nicely. And we had them present them in front of the department chief, which put some pressure on them, but I think it was all good. So we've taught 8 iterations of this course, 3 of them at Penn, and the Penn cohort is the one from which I'm presenting data today. We had 38 pathology residents, fellows, faculty, and a few others. And you can see most of the participants were trainees, but we've had a lot of participation from faculty, including some really senior folks as well. Before the workshop, we surveyed participants about their confidence in their programming skills. And a lot of people indicated that they felt like coming into the course, they didn't know enough about programming to really benefit from the material. So here, this is graded, the survey is graded from 0 to 10, where 10 is completely agree, 0 is don't agree at all. The question was, I'm concerned I do not know enough about programming. And you see a whole bunch of people were very concerned about this. But when surveyed after the course, no one felt that the required knowledge about programming was too high for them to follow. And while I like to think this is because of my superior teaching ability, I think it's more likely a consequence of the human-friendly idioms of the Tidyverse, or maybe a mixture of the two. Overall, participants felt like the course achieved its stated objectives. People felt more confident in their grasp of the idea of reproducibility and their ability to load data into R, to transform data, and to create plots. On a scale from where 0 is unsatisfying and 10 is outstanding, the workshop was rated an average of 9.6. So I'd like to invite you all to take a look at the materials for the course. They're freely available at this URL. So we've also given this workshop or a version of this workshop at this year's PI Summit. And we have been invited to come back and do it again next year. So we're looking forward to that. So if you wanna sign up for this workshop, we'd be super excited to see you back there. All right, to recap, so we introduced the idea. This actually brings me to the end. This is my last slide. We introduced the idea of computational documents and R Markdown. Again, these are plain text files with embedded executable code and can be turned into automated reports and dashboards. We talked about the Tidyverse, which is a human-friendly programming language for data analysis, and we talked about the course in reproducible clinical data analysis with R&R Studio, which is a one-day workshop for clinicians to learn how to write computational documents. And so with this, we have a lot of time for questions. So what are your questions at this point?